(2.4.1) Light harvesting. One of the critical factors to evaluate the photothermal performance is the light harvesting ability that reveals how well a photothermal material absorbs the energy of incident photons. The light absorption is an important process of light-to-heat conversion. Absorptance is defined as the fraction of the energy of incident photons that is absorbed by a material. The absorbed energy for a certain material depends on the range of absorption over the spectrum of the incident light and the intensity of absorbance for each wavelength. By integrating the absorption intensity of the photothermal material over the spectral range, the absorptance can be calculated by the energy ratio of the total absorbed light to the incident radiation. At an incidence angle of theta, the overall absorptance A, theta, of a light absorber can be expressed as, where P, lambda, lambda max, and lambda min represent the wavelength-dependent radiation power and the maximum and minimum wavelengths of the incident light, and R, theta, lambda, and T, theta, lambda, stand for the total reflectance and transmittance of the absorber at the wavelength lambda, respectively. According to this equation, the absorptance can be enhanced by reducing the transmittance and reflectance of the photothermal material. Moreover, broadband light absorption is crucial for light absorbers to harvest enough light for obtaining high light-to-heat conversion efficiencies. For the case of photothermal materials dispersed in homogeneous semi-transparent media, light absorption is a cumulative process with an exponential decay that can be described by Beer-Lambert's law as I equals I0 E, kappa Cl, where I and I0 represent the light radiation intensity after and before the absorption. Kappa stands for the extinction coefficient, C is the particle concentration, and L is the length of the optical path. To further determine how much of the light is absorbed by the material, absorbance A is defined as the attenuation of the incident radiation power. It can be calculated from the transmittance T, as the absorbance is therefore proportional to the extinction coefficient of the absorber and the amount of the absorber per unit area. The extinction coefficient is the intrinsic property of the absorber. It depends on the material, size, and shape.